So our next presenter is Dr. Christiana Ade. She is a remote sensing scientist and postdoctoral fellow at NASA Jet Propulsion Lab. Her current work is centered on advancing science and applications related to the Surface Biology and Geology satellite mission, which will launch within the decade. She earned her PhD in environmental systems at University of California, Merced. Merced. Her dissertation focused on remote sensing derived mapping of invasive floating aquatic vegetation abundance and phenology, as well as habitat mapping for an endangered fish species. Please welcome Dr. A.
Thank you for the introduction. Just to reiterate, because NASA really wants me to reiterate this research was when I was a PhD student at the University of California, Merced. It's not my current research. I don't know if that's because they want you to know who to come after if I say something wrong or not, but yeah, so we have the challenge to promote well-planned and healthy, resilient aquatic ecosystems. And this can really only be done with remote sensing observation technologies. But I do want to reiterate that remote sensing enables us to support field measurements and field monitoring and restoration. So remote sensing and field studies are definitely reliant on each other. There are three typical types of platforms, and I'm going to be discussing some of these today when we're talking about mapping vegetation from space or from airborne. So satellites, which tend to have larger pixel sizes, but they have very high repeat visit times because they are in orbit. There is a planned repeat visit time. Then you have airplane mounted hyperspectral sensors. So hyperspectral just means that you are collecting data in a lot of bands. So this is a very high quality data set. This does allow you to also have smaller pixel sizes in the satellite because you are flying the plane closer to the Earth, but because of cost, there are longer revisit times. And then you have unmanned aerial mounted aircraft. This is the smallest pixel size of the three. You can have like RGB cameras or hyperspectral data from them as well, and that allows you on-demand flights. So I've been asked to talk about kind of like this invasion story in the Sacramento-San Joaquin Delta, which is a very important spot for California because it supports a billion-dollar agricultural industry, and it is one of 25 global hotspots for biodiversity, but it is very highly invaded at the moment, and it is one of the most managed and vulnerable ecosystems to climate change. So as of 2018, invasive species covered 40% of delta waterways. Two of the main invasive floating species are water primrose and water hyacinth. There are a number of invasive submerged aquatic species as well, but I'm not really going to be talking about those today. And so despite the fact that one of my coworkers here is smiling out in the field, we're not very happy about the increase in water primrose. It has increased fourfold from 2004 to 2016. And it's actually starting to encroach into native emergent marshes and choke those out, replacing the marsh vegetation. More historically, the way that we have studied and mapped these areas has been using these high resolution annual snapshots with that airborne imaging spectroscopy data. That's the hyperspectral data. So as you can see, you get these really nice spectral response curves of reflectance, and with these different features, so you can see there's like different dips in that graph that relate to different species. You can actually start to separate them out at the genus level. As I said, water primrose is encroaching on native emergent marshes, and using that airborne imaging spectroscopy data, this becomes really clear. You can see that yellow really start to take over, really fill in all those waterways, and then actually go into the marsh by October 2016. But as I said before, these flights are pretty costly, and the annual acquisitions actually make you miss key stages in the vegetation growth cycle. So how about we fill those in with some satellite data, which has a high repeat period. So in this talk, I'm going to be using Sentinel-2, which is a European Space Agency satellite. It collects data in 12 bands, has a 10-meter spatial resolution, and it collects data every 5 days when you're not counting for cloud cover. So the first question I had is, we know that we can separate out water hyacinth and water primrose at the airborne hyperspectral level, but can we do this also at the multispectral Sentinel-2 level? Is the spatial resolution good enough at 10 meters as opposed to 1.57 meters, and is the spectral resolution good enough? So you can see that under that Sentinel-2 plot on your left-hand side, no wait, sorry, right-hand side, you don't have as many of those like absorption features or those key little bumps that you might need to distinguish vegetation types. So for this classification, I had 6 different classes. That was water primrose, water hyacinth, emergent vegetation at the community level, riparian vegetation at the community level, SAV, and non-photosynthetic vegetation. And if you just look at some of these example spectral responses, it does look like we would be able to separate those out from each other. In order to do this, we followed a similar procedure from the airborne imaging spectroscopy mapping data sets. So what we did is we selected the closest Sentinel-2 overpasses to those airborne imaging flights so that we can compare the two mapping outputs. So that was from October 2018, September 2019, and July 2020. And we adjusted some field data GPS points collected for those airborne imaging spectroscopy flights to the Sentinel-2 pixels. So that's just kind of like shifting them over to make sure that they are representative of those classes. And then we used the spectral response from Sentinel-2 as well as important water and vegetation indices to build 3 random forest models and test accuracy. So by looking at random forest, we were also allowed to see which spectral indices and which wavelengths were really important for separating out these different vegetation types. And that is, of course, important when you're looking ahead and trying to decide what satellites can you use or what kind of drones do you need to separate out these different vegetation classes. So for all 3 models, we did have an overall accuracy of above 87%. And some of the important bands were green, near infrared, shortwave infrared, and some of the vegetation indices. And so now looking at 2 maps where we're comparing Sentinel-2 on one side to the imaging spectroscopy results, we can see that they actually match up pretty well, and that you can detect so the purple patches are the water hyacinth from the water primrose, which are the yellow patches. So we're really, really excited about that. More information about this work is in this paper that I published for my dissertation in the journal Remote Sensing. So feel free to have a look at that if you want more information about the procedure and results. But now, we have these maps, and I previously mentioned that satellite data does give you that repeat period that can give you a lot more information than if you just have one annual flight. So how can we use the high temporal frequency of Sentinel-2 to understand more about the invasion process? And I was looking at this from the perspective of phenology. So invasive species oftentimes have phenological advantages over native species or other competing invasive species, and that can be explained by different hypotheses. So one would be vacant niche is where the exotic species blooms or leaves out when native species is not in bloom. Hypothesis B would be it blooms up earlier or greens up earlier. Hypothesis C, niche breadth, it has a longer duration of growth, and hypothesis D is it has high plasticity and can kind of like adapt to different environments and climates better than competing invasive species or native species, and that's like very important to consider in the face of climate change. So using Sentinel-2 data, I wanted to look at what are the differences in phenology between water primrose, water hyacinth, and emergent vegetation. In order to do this, we use a vegetation index. So I used EVI, and what that does is look at different parts of the electromagnetic spectrum that are corresponding to like high chlorophyll, and then the structure of the plant. So if you look at the like very bright green vegetation spectral curve, you can see like uh, at one of the bands, the near infrared band, that's the one shown in brown, it's very highly reflective, but then if you look at the brown vegetation, that decreases a lot. So I'm really trying to characterize this like red edge with this index. But essentially, this is just an index of plant greenness. So what you do is what we computed EVI for each date in our time series, and we look at a time series from 2018 to 2020. So you have an EVI for each one of those dates, and then you do a Gaussian asymmetric fitting function, and then from that you can extract phenology metrics. I looked at 5, so that was the start of the growing season, the end of the growing season, the length of the growing season, and I'm not going to talk about the last 2, but we did investigate the rate of increase and the rate of decrease. And if we look at those 3 vegetation types, we do see that there are very different phenology curves for each type. And right now I'm just going to talk about the start of season and the length of season. We looked at this for 3 different sub-study areas in the Delta. So if we look at start of season, you see that water primrose, which is in yellow, has an earlier day of year, so earlier start of season than water hyacinth and emergent vegetation. And then if you look at this next plot, which is length of season, it has a higher number of days. So water primrose starts growing earlier and grows for longer than either emergent vegetation or water hyacinth. So it shows, back to that plot that I showed you of different hypotheses related to invasion, niche breadth, and priority effects. But what's really cool about this is we can actually like start looking at the maps, and that gives us additional information. So I'm going to talk you through this example here, which is where I'm describing 2 types of water primrose and 2 emergent vegetation types. So the types of water primrose, the types of emergent will be cattail in this kind of yellow color, and what you're looking at here is just the start of season. And then tule, which is the more red area, and then the 2 primrose will be this terrestrial primrose, which is where it actually has started to encroach on the marsh, and that is yellow as well. And then the water primrose, which is just where it's growing over open water. So if we start to look at the curves, we of course see again that water primrose does show us niche breadth and priority effects, but there are different responses within these class types. So aquatic and terrestrial primrose have different phenologies. Aquatic tends to have start growing earlier and then also grow for longer than the terrestrial primrose. And then the start of season for emergent cattail is closer to primrose than the start of season for emergent tule. So you're just kind of looking in that little box area. We're thinking that because of that, perhaps the EMR cattail might be more resistant to actually experiencing this marsh encroachment problem with water primrose. So as I said before, water primrose may have a phenological advantage over its competitors explained by priority effects and niche breadth, and then environmental plasticity, because we did see that occur regardless of which sub ecosystem we looked at. I'm hoping this is, looking at metrics like these are important for management because it might help you decide when you want to use your pesticides, and then it also helps with restoration projects if we get better understanding of how long these things are growing, where they're growing, so that when you restore a site, you can kind of mitigate that before it even happens. I don't know why that's here. Oh, yeah. And so I wanted to really briefly, because I did say I was going to mention about drones, talk about one of my former lab mates' research where he, if you're thinking right now like 10 meters is actually still too coarse for you, you can use drones to map these different invasive plants. So he used a nano hyperspectral pro and compared it to those same imaging spectroscopy maps that I did. And in doing so, if you look at the nano map, you can see that there are some water hyacinth pixels that he discovered, so that's the purple color, that are just not present at the 1.7 meter spatial resolution. And when we went into the field, that was in fact true. There was water hyacinth there that we were not detecting with the airborne craft. If you want to know more about his work, here is his paper. He also includes a feasibility assessment relating to the different costs of doing the aircraft versus the drone approach and processing times. And then kind of in the same vein of this morning where it was like, oh, you should also be paying attention to the different environmental parameters of your study site. You can use remote sensing for that as well. So there are thermal infrared measurements where you can use that to map surface water temperature. And then you can also use these same optical instruments to do different water quality parameters like turbidity and chlorophyll. And then some other NASA products, they recently launched the SWAT satellite, which will be the first satellite to have a river discharge project for rivers that are greater than 100 meters wide. There is the emit sensor and the ecostress sensor on the International Space Station at the moment. And as I said before, a lot of my work right now is going to support the surface biology and geology mission, which is a combined imaging spectrometer thermal mission. So just to highlight what some applications of that would be, this is an example from the San Luis Reservoir in California, where you have, I'm using the precursors emit and ecostress on the International Space Station to make these maps where it's chlorophyll A, and you can kind of see a chlorophyll bloom happening in the middle of the lake, and that actually corresponds to higher surface water temperatures. So something to take away from this is also, depending on your ecosystem or your like mapping question, each one of these platforms has its own trade-offs, whether it be spectral resolution, where current satellites have lower spectral resolution than is available for air-mounted or drone-mounted hyperspectral, but they do have better revisit times, and then you can get finer pixel resolutions with the latter two. And then with that, I will take any questions. Those are the two papers that I mentioned, and I would just like to thank the Delta Stewardship Council for funding a lot of this work.
I was curious, so did the amount of error change depending on the season? As the seasons went by, did the error change? The amount of error you got from identifying the text change?
You're saying because I looked at the like 2 fall images and 1 summer with the classification mapping? Yeah, I would say that the summer was a little bit less accurate because when these things are like in full leaf out, they're more spectrally similar, but it wasn't that much. It might have been like 2% difference, so it's still very good. In terms of, and I didn't mention this, SAV, like the real important thing that decreased accuracy was actually the influence of tides, not the influence of season. So if there is like more water cover and a higher tide, you cannot detect it as well, but that's kind of expected. Yeah.
With the Sentinel-2 data, did you find that there was a minimum patch size for detection, especially when comparing it to the drone data?
So you generally want so like let's say like my spatial resolution of Sentinel-2 is 10 meters, so you kind of want it to be like 3 times the size of that, or like 2.5 is generally what you're aiming for. I did find a couple patches that seemed to be accurately mapping where you only had like 2 or 3 pixels, but I would kind of like caution against that. Sure.
I'd just be curious to get your thoughts on potential uses of the SWAT satellite data for AIS management.
I just plugged that one because a lot of people don't know about it. I don't know that much about SWAT myself, but I think that it could be potentially interesting because it would be like spatially resolved discharge to look at places where, like, I don't know, water might be slower, and then maybe like invasive species could more likely establish there or something like that. But it would also probably be important when you're looking at some of those other water quality variables, like how does discharge relate to an increase and decrease in turbidity or something like that. Sure.
So when you were doing your random forest classification, doing that model, did you inform the model using the airplane data or just the sentinel data?
Just yeah, we just still had the mapping outputs from the airborne data so that we could make sure that our maps looked good. Sure.
I was curious why the presentation you said the drone data was the higher spectral sensors, the drone data was low quality compared to the other sensors when the drone was able to detect more in nectar project, but for your fractional.
Yeah, so what I mean by lower quality there is a lot of drone instruments, even if they are hyperspectral, might not go into the shortwave infrared, which makes it like lower quality because that, as we determined in several experiments, like it is very helpful to have those bands. And then also drones are a lot more reactive to like wind perturbations than aircraft would be. So you do need to be more careful about that. And then because of that, your data can be a little bit noisier. So you might have to run some like smoothing on those spectral curves before you use them. But that's kind of what I meant by lower quality.
I think there's time for one more question. Anyone else? Anything else?
Okay. Do you believe that in the future they'll be able to like clearly identify? Do you think as technology advances, we can one day just rely on satellite imagery for identifying in terms of invasive species? Again, aesthetically invasive plants.
So you mean like just get rid of any field operations? I would say that like field operations are always very nice and necessary for validation of your products and training of your products. And then also just, yeah, like getting an understanding of the accuracy. There are certain things that like satellite data probably won't ever be able to do in terms of spatial resolution. So if you're really trying to get down at like sub 1 meter because you want to do like early prevention methods, then no. But I still think like it's just like a useful tool, and I think field data is still a useful tool.
Thank you.